Hello everyone and welcome back to Tech Mind Guru. I'm your coach Supratim. Today we are diving into DSA lecture 33. So get ready because today is all about mastering queues. Consider this is your ultimate FIFO data structure guide. We are going to cover everything starting from a simple ticket counter analogy all the way to solving the classic sliding window maximum problem. So what is a queue? So let's start with the physical queue. Think of waiting in line for a ticket. The golden rule here is simple: first in, first out, also known as FIFO. When you enter the line, you join the rear end, that is from the back side, and when it's your turn to exit, you leave from the front end. Right? This same logic applies to digital flow as well, like an incoming calls queue being distributed to agent 1, agent 2, agent 3. So to manage this system, we rely on our core operation toolkit. So we use Enqueue to insert an element from the rear end. We use Dequeue to remove data from the front end. Also, we can easily check the ends using front to get the data at the front and rear to get the data at the rear end. IsEmpty check if the queue is empty or not. And you know what is the best part? All of this operate in constant O1 time complexity. So how do we actually build one? We can use dynamic arrays and linked list. If we use arrays, we manage pointers for the front and rear using logic like returning our array at index f-1 when we dequeue. So let's see how. So as we know, in stack, we used to keep top is equal to -1 initially. In a similar fashion, we will keep f is equal to 0 and r is equal to -1. And whenever enqueue an element in queue, you will increase your rear pointer. So your rear will be initially somewhere here and your front will point to here. So this is the same reason why isEmpty method is checking whether your f is greater than equal to r or not. And whenever you will enqueue an element, you will do r++, and after that you will keep that element into a of r. Similarly, when you will do dequeue, you will first check the underflow condition and then you will move your front pointer and you will return the previous pointer by a of f-1. So let's see this dry run with this code. So suppose you first inserted 3. So when you enqueue 3, your r will become 0 from -1, right? And in your a of r, what will go? The element will go to a of 0. Suppose you insert or enqueue the next element, which is 5. Now your r will become 1 and now your a of 1 will become 5. Similarly, when you enqueue 8, your r will become 2 from 1 and your a of 2 will start holding the value as 8. Now when we want to dequeue, since dequeue will also happen from the front side, so this time we will move our front pointer from here to here. So when you dequeue, you will first check the isEmpty method whether the queue is empty or not to check our underflow condition. If the queue is empty, we will return -1. But in this case, we have already inserted 3 elements. So our r is pointing at 2 index. And since we have not deleted anything, our f will keep on pointing to the 0th index only. So when we dequeue, we will increase our front pointer. So now our front pointer will start pointing to the 5. And what we will return? We will return a of f-1. So what is new front now? 1. And what will be a of f-1? Which will be a of 0. So what is there in the a of 0? 3. So 3 will get dequeued from the queue. Similarly, whenever you have to find the front element, you will do a of f because f is pointing to the front element, and whenever you have to find the rear element, you will just do a of r because r is pointing to the rear element. So this was how to build a queue using dynamic arrays. Let's see how to build a queue using linked list. So for building a queue using linked list, you will have 2 pointers, one pointing to head and another pointing to tail of the linked list. So whenever you will enqueue, you will insert at tail. So what will be your tail now? So tail.next was initially null. So a new node will be created using new node of x method. And now your tail.next will start pointing to the new node, and finally your new node will become the tail now. So a new node will become the new tail now. So whenever you have to do dequeue, you will delete from head. So you will simply make head is equal to head.next. And when you have to check isEmpty, you will just see if head is null or not. If the head is null, that means the stack is empty. And anytime you have to get your front element of the queue, you will just do head.data. And whenever you have to get the element from the rear end, you will just do tail.data. So deleting or dequeue will happen from the head by using head is equal to head.next, and inserting or enqueuing into the linked list will happen at the tail, where you will first initialize the new node, second you will do tail.next as the new node, and finally you will assign the new node as the new tail. And now your new node will start pointing to null. But let's look at the time complexity showdown. If we build our queue using a linked list, we map the enqueue operation to the tail, as we have already seen, and the dequeue operation to the head. So by inserting at the tail and deleting from the head, we always guarantee O of 1 time complexity across all operations, except if you do deletion from the tail, the operation will be O of n. So let's trace a quick example to see if you can predict the final state or not. Suppose you have to enqueue 3, 7, 12 in your first operation. So 3, 7, 12 will go inside the queue, right? Now suppose you called delete. So your 3 will get deleted. Again you call delete. 7 will get deleted. Again you enqueued 8 and 3. Now in your queue, 12, 8, 3 will be present. So your final result will be 12, 8 and 3. Similarly, suppose if you enqueue 4, 4 will get inserted, then delete, 4 will get deleted, then you enqueue all this 9, 3, 7, 11, 20. So all this will get inserted inside the queue, and when you call delete, your delete will get called from the head. So 9 will get deleted. So your final result will be 3, 7, 11 and 20. Now let's tackle a classic interview problem that how to implement queue using stacks. So suppose this is your array of operations where you will enqueue 5, then 4, then 7, then 9, then you will call delete, then 8, then 10, then delete again. But you cannot use queue here. You have to use stack. So if you think the enqueue is easy, if you take stack, right? So you will just push X into stack and that will be O of 1, right? But for Dequeue, we will hit a wall because in stack, when you start filling the elements inside the stack, it will be from bottom to top. So the element which will go at the last will stay in the top. But in case of queue, we want that element to Dequeue at the last only. So how we will do that? So here we will use two stacks. So we will take another stack, stack 2, where we will pop from the stack 1 and we will push into the stack 2. Now 9 will come here, then 7 will come here, then 4 will come here, and then 5 will come. And now if you pop out from the stack 2, you will get the result in the proper order. So this is called a Dequeue strategy, where you will transfer all elements from stack 1 to stack 2. Now you will remove the top element in stack 2, which will be our front. So let's see the code for the same. So suppose you have to insert 5, then 4, then 7, then 9. So when you called enqueue method, it will push that element into stack 1. So stack 1 will be holding 5 now. Similarly, for the next element 4, it will again call enqueue. It will store on the top of 5. Similarly, 7 will get stored on the top of 4 and 9 will get stored on the top of 7. Now, when you will call Dequeue method in your problem, that time first you have to check whether your stack is empty or not. So in this case, we have to check whether both the stacks are empty or not. We will check whether stack 1 is empty and whether stack 2 is also empty or not. And if this condition doesn't work, we will come to the next block. We will check if only stack 2 is empty or not. Since initially the stack 2 will be empty, we will call a move method. So what will the move method do? It will simply put all the elements from the stack 1 to stack 2. So for that, we are running a while loop, which will check if the stack 1 is empty or not. If the stack 1 is not empty, we will push the element to stack 2 by popping it from the stack 1. So 9 will come here, then 7 will go here, then 4 will come here, and finally 5 will come. And when this move method is over, we will come out of this while block when stack 1 will be empty, and finally we will return stack 2 dot top. So whatever went first inside the stack, that only coming as the first element from the stack. So what is the time complexity of this? So this perfectly introduces the magic of amortized analysis. So if you see the above code, which we just saw, so we might have a high cost O of n move operations, but it is immediately followed by low cost O of 1 pop operation as well. Suppose if the move takes O of k times, then the next k Dequeue operation will take only O of 1 time. That is, one time your time complexity will be O of k. That is when you transfer all the elements from stack 1 to stack 2, and after that all the Dequeue will happen in O1 time complexity only. So if you want to see again, you will see that when you called Dequeue for the first time, that time the stack 2 was empty, right? And that time we moved all elements by running a while loop from stack 1 to stack 2, and we stopped when the stack 1 was empty. So when this move method works, all the elements from stack 1 will come to stack 2, right? Next time when you call Dequeue, you will see the elements present in the stack is already there, right? So this if block will not work, so we will simply pop from the stack 2. So first Dequeue took O of k times, but from the next Dequeue, it's like O of 1 time only, because our code will not enter in this block to call our move method. So move method will run 1 time only. So because of this balance, our average time complexity evens out to O of 1. Next, we will level up by understanding how a doubly ended queue, which is also known as Deque, works under the hood. So doubly ended queue is usually implemented using a doubly linked list, which we will definitely learn in our upcoming classes. So this will give you the new powers like enqueue in the front, Dequeue from the front, enqueue from the rear, and Dequeue from the rear. And all this operations time complexity will be O of 1 only. We can insert from front, delete from front, insert from rear, and delete from rear. So earlier you have seen that when you want to delete an element in a normal queue, that deleting from tail was time complexity O of n. So to resolve this, we just use doubly ended queue, which is internally implementing doubly linked list and reducing our time complexity to O of 1. So why we understood this enqueue front, enqueue rear? Because we need this power for our boss fight. That is in the next question, which is of sliding window maximum element. So in this problem, you will be given an array A and an integer k, and you have to find the maximum element in every contiguous subarray of size k. So your window size will be of k length. Suppose initially your k is equal to 5. So in the first iteration, what is the max element from this subarray? 8, right? So 8 will get stored. Similarly, when your subarray becomes from here to here, what is the maximum in the subarray? It will be again 8 only. Similarly, when you move to this subarray, that is from 5 to 2, your maximum is 7, right? Similarly, when your subarray is from 6 to 0, what is your maximum element? 7 again. And similarly, when your last window will start, that is when your subarray will start from 7 and end at 3, at that time also we will get 7 as the maximum element. So this will be our answer. So this is a lead code problem. The link I will mention in the description as well. So let's see the ON optimal solution for the same. And here is the secret. In this, you will store indices and not the data in your Deque, which is doubly ended queue. So let's understand the code with the same example given in the question for our dry run. So initially, we will just check the first window as you have already remembered from your sliding window, that your first window is checked separately, and then next k-1 windows are checked after that. So suppose let's take a queue for the same, for storing the indices. So initially your code will start from for I is equal to 0 to k-1 and k is 5 here. So it will check whether the queue is empty or not. Since the queue is initially empty, so this while loop will not work for this index. Then we will simply insert from the rear. So 0 will get inserted here. Now again we will come to this one. We will check whether a of q dot rear, which is 0, is lesser than equal to a of I or not. Since 1 is lesser than equal to 8, we will dequeue from the rear. So we will dequeue this element from the rear. So this element will be gone now. Now again we will check whether the queue is empty or not. Since the queue is empty, our while loop will break. We will again enqueue rear. What is present in the rear? We will insert 1. Similarly, for the next iteration, which is at 2, we will again check whether queue is empty or not. So the queue is not empty. We will check whether a of q dot rear, which is a of 1, is lesser than equal to a of 2 or not. So what is present in the a of 2? 5. And what is present in the a of 1? 8. Right? Since 8 is not lesser than 5, so this while loop will not work. We will again insert the index in the rear. So we will now insert 2 here. Again, our for loop will point to next index, which is 3. We will check whether queue is empty or not. Queue is not empty. We will check what is present in the queue rear. The queue rear is having now 2, right? So we will check whether a of 2 is lesser than equal to a of 3 or not. Since a of 2 is 5 and 5 is lesser than equal to the current element, which is a of 3, which is 6. So we will dequeue again from the rear. So 2 will get dequeued. Now what is our new rear? It will be 1. So now again we will check the element present in the rear, which is a of 1, is lesser than our current element or not, which is a of 3. So what is there in the a of 1? 8, right? And what is present in the a of 3? 6. Since 8 is not lesser than equal to 6, so this while loop will not work, and we will come to the next block and we will enter that index into our queue. So now we will insert 3 into our queue. Now again outer for loop will move to the next element, which is 4, and what is present in the rear? 3, right? We will check whether a of 3 lesser than equal to a of 4 or not. So what is there in the a of 4? 7, right? And what is present in the a of 3? 6, right? So this condition will be again true. So we will dequeue the element from the rear. So now again, what is the rear element present in the queue? A of 1. So we will check whether a of 1 is lesser than equal to a of 4 or not. We will see that 8 is not lesser than equal to 7. So we will come out of this while loop and we will enqueue the next element, which is 4. So let's move this 1 to here so that we get more space to write. So now this 4 will be coming to the rear, since we only enqueue at the rear only. And finally, since it reached 4, this for loop will break and we will print a of q dot front as the maximum element in the first window. And what is q dot front? Which is 1, right? Because rear is now 4. And what is a of 1? 8. So we will print 8 in the answer. And then we will move for the remaining windows, which will start from k to n-1. Now, what is k? 5, right? So this loop will start from 5 and it will go till 8. So again, the same piece of code is copy pasted here. Here we will check whether q is empty or not. Since q is not empty, we will check whether q dot rear, which is a of 4, is lesser than equal to the current element or not, which is a of 5, right? And what is there in a of 4? 7, right? And what is there in a of 5? 4. So this condition will not work. So we will come out of this while loop and we will enqueue the index in the rear end. So 5 will be enqueued at the rear end. Now we will check whether q dot front is equal to I minus k or not. Because if q dot front is equal to I minus 1, that means we have gone out from that window. So what is there in the q dot front? 1. And what is I right now? It will be 5. And 5 minus 5 is not equal to 0. So this condition will not work. So we will not dequeue anything from the front. And we will print a of q dot front. So what is there in the q dot front? It will be a of 1. So 8 again will get printed. In the next iteration, we will move to this 6. We will check whether q is empty or not. Since q is not empty, we will check the next condition. What is present in the q dot rear? 5, right? So we will check whether a of 5 is lesser than equal to a of 6 or not. So what is present in the a of 5? 4. And what is present in the a of 6? 2. Since 4 is not lesser than equal to 2, so this while loop will not work. We will not dequeue anything from the rear and our control will come to this code. Now we will enqueue the index in the rear. So we will keep 6 in the rear end. And after that, we will again check whether q dot front is equal to I minus k or not. Now, what is there in the q dot front? It is 1 only. And what will be I minus k? It will be 6 minus 5, which will again come as 1. So this condition will work now. So we will dequeue this element from the front, since we have crossed this window now. And once we dequeue the front, we will print the q dot front. And what is present in the q dot front now? 4. And what is a of 4? A of 4 is 7. So we will print this element as 7. Now, in the next iteration, we will move to this index 7. We will check whether q is empty or not. Since the q is not empty, we will check a of q dot rear, which is a of 6, is lesser than equal to a of 7 or not, which is the current element. Since 2 is not lesser than equal to 0, so this condition will not work. So we will enqueue the index into our rear end. So 7 will get inserted into our rear end. Now we will again check q dot front, which is 4, is equal to I minus k or not. What is I right now? 7. And what is k? 5. Since 4 is not equal to 2, so this if condition will not work. We will again print the q dot front. And what is present in the q dot front? It is a of 4. And what is a of 4? 7. So we will again print 7. Now finally we will move to the last index, which is 8. We will check whether the queue is empty or not. Since the queue is not empty, we will check the next condition. Now what is present in the queue dot rear? 7, right? We will check whether a of 7 is lesser than equal to our current element or not. What is our current element? A of 8, which is 3. And what is a of 7? 0. Since 0 is lesser than 3, we will dequeue from the rear. So we will dequeue this element. So what is our new rear now? 6. So now we will check whether a of 6 is lesser than equal to our current element or not, which is a of 8. And what is a of 6? That is 2. So we will check whether 2 is lesser than equal to 3 or not. Since 2 is lesser than equal to 3, we will again dequeue from the rear. So we will again dequeue 6. Now what is present in the a of 5? 4. And what is present in the a of 8? It will be 3. Since 4 is not lesser than equal to 3, we will come out of this while loop. Next, we will insert that index into our rear. So 8 will be inserted in the rear. Finally, we will check whether q dot front, what is present in the q dot front? 4. And what is I minus k? Since I is at 8, it will be 8 minus 5. It will be equal to 3. So since 4 is not equal to 3, again this if block will not work. We will print a of q dot front. So what is present in the q dot front? 4 only. So what is a of 4? 7. So finally, it will print the maximum from each window as 88777. So what is the time complexity here? Since we are running 2 for loops, and inside that for loop, we are running while loop also, but that while loop will be again enqueuing and dequeuing the same elements which are present in the array. So this will be like similar concept we learned in case of stack. So here the time complexity is O of k, and similarly for this one, our time complexity will be O of n minus k. So our final time complexity will be O of n, and since we are taking q of k size at least, so our space complexity will be O of k, since k is the size of the queue which we need for solving this problem. And just like that, you conquered queues. So let's quickly review the master checklist that what we have learned today. So initially we learned about FIFO mechanics, that is first in first out mechanics, and how using queue all Enqueue, Dequeue, IsEmpty, rear and front function are giving O of 1 operation. Then we understood how to build a queue using dynamic array as well as linked list implementation. And next we saw how to implement queues using stack, and then we understood amortized analysis via stacks, and we learned about doubly-ended queue, also known as Deques, and we finally solved the sliding window maximum problem by cleverly using Enqueue front, Enqueue rear, and Dequeue front and Dequeue rear. So with this, we have come to the end of the lecture. So if you found this video helpful, hit that like button and subscribe to TechMindGuru. In our next lecture, we will deep dive on tree structure and traversal. Till we meet again, keep learning, keep coding, and keep optimizing.